Where am I?
It's live.
Yeah, it's
like we show up live.
I tested it before, but now. Okay. Okay. So here
we are.
Okay. I'm very sorry.
No problem. Yes, on the thermosets, you can recycle them. However, with the energy intense and technically complex processes, on the thermoplastics, you have thermoplastic materials as a matrix. You can recycle them in a mechanical way by cutting or milling. And the important thing here is that the fiber and the polymer are recovered. So you can recover both at once. You have pre-impregnated fibers, which is already pretty good. On the one hand, because it's already there. The technical barrier is comparably low, and for sure, low technical barrier means also a quite cost-efficient process. And from the ecological point of view, the energy consumption for making this is much more reduced compared to the thermoset recycling. And this is, let's say, the high-level introduction of the processes that we did, and that Tim is going to present now with the next slide. And hand over to Tim. The stage is yours. Thank you.
Okay. Thank you very much, Florian. And once again, very sorry for the interruption. Well, with that, now let's have a look on the technical aspects and challenges of mechanical recycling of those CFRTPs. And let me also show you some products that can be made out of this valuable waste material. As Florian has already shown in the introduction, the CFRTP production entails different steps where each of them produces a certain amount and also a certain type and quality of waste. And for our purposes of recycling, the quality of the different waste fractions is mainly defined by the shape of the scrap. I will show later that this is basically defined which way to go with the scrap. The pictures that you can see here on the slide shall give you an impression what kind of scrap mixtures accumulate during production. You can see, for example, a random selection of small and big pieces of cut-off tapes from the fiber melt impregnation and tape assembly steps, as well as step of unidirectional tape rolls, which build up during production start. And further downstream, big and small pieces of sheet scrap result from the tape consolidation and subsequent edge trimming processes as well. Now, as a key for efficient recycling, proper waste management is of utmost importance. And this includes that each of the different scrap qualities are collected separately, and also that the waste is collected by product type. For example, by different polymer resins or fiber types, such as glass and carbon fibers. With this, we ensure that the minimum of the generated waste will end up unused or unrecycled. And in the end, the main target is, of course, to avoid the incineration and landfill, something that will be legally prohibited in the near future anyways. And as said earlier, each of the sorted waste qualities then qualifies for one or more specific recycling routes, including the size reduction and the post-processing. And I would like to emphasize that we are not doing this just by ourselves, but we are working together with local recycling partners who have the right equipment, the experience, and required licenses to turn our production scrap into new products. Okay, as said, different ways of mechanical recycling can be applied based on the quality and shape of the composite waste fraction, where each process has its advantages and disadvantages. The selection of the right technique should be made based on the requirements of the following step to turn the scrap into new products, like, for example, compression molding or compounding. Firstly, shredding is a common technique for size reduction of any sorts of solids. The advantage of this process is that a broad range of different scrap qualities can be handled. However, depending on a subsequent processing step, the technique can constitute certain limitations. For example, compression molding of the shredded composite into new sheets might be doable, even the material is quite coarse and inhomogeneous. But on the other hand, for using the scrap as filler material in compounding, the size and the homogeneity of the scrap usually needs to be adjusted to match the specifications of the feeding equipment. This means that, for example, several subsequent shredding cycles or sieving steps might be necessary, which eventually reduces the overall efficiency. Another process we have looked into is to granulate the composite waste. And this process ideally results a sort of compacted scrap intermediate with a reduced amount of loose fibers. Similar to the shredding process, a broad range of waste qualities can be used, and sheet molding with the granulate is equally possible. However, depending on the degree of compaction, using this type of granulate can be rather challenging to use in compounding due to the limited flowability of the material. You might need to add some amounts of fresh polymer, for example, as sort of glue to improve this processability. And then as third option, we have checked milling, turns all sorts of composite waste into powder form. The powder is easier to process on a compounding extruder, but on the other hand, there's the risk of electrical shortcuts due to the electrical conductive carbon fibers and requires a proper machine installation. This is, by the way, something that applies to all mechanical recycling techniques of carbon fiber containing materials. Also, the milled composite powder contains high amount of respirable loose fibers in the submicron scale, which are hazardous and add another risk for the operator. But most important, from a product perspective, milled composite raw material disqualifies for making super stiff compounds due to the lack of sufficient fiber length. And with this, you sacrifice, of course, one of the key benefits of this valuable carbon fiber raw material. And here, last but not least, guillotine cutting is another possible way of size reduction, which results in neatly cut chips or flakes. In this process, mostly tapes are recycled because sheets are just too stiff to be cut properly with the knives of the machine. And this technique is the most labor-intensive, but yet the most controllable of the here mentioned options. The chip size can be adjusted by the positions of the knife, which result then in tailored fragments and fiber lengths. Here, also additional sieving steps to remove loose fibers might be needed as well to ensure proper post-processing. And the so obtained flake material can then be used for the production of different new products. And let's have a look now on these products. So once the composite waste has been processed into shreds, granules, powders, or flakes, as just shown, a variety of possibilities open up to turn them into new products, such as simply using the scrap as core material of new CFRTP sheets, as shown on the left. This brings down the material costs, but goes along with the reduction of mechanical performance compared to virgin composite sheets made from unidirectional tape layers. Another possibility is compression molding of the size and shape-defined flakes from the guillotine cutting process to produce sheets with a unique so-called marble appearance, as shown in the middle picture. And Florian will talk about this in more detail a little later on. The third way to recycle composite scrap is compounding. For us as Covestro, certainly the most familiar business in terms of the final product. Technically, the size-reduced waste is mixed with virgin polymer and further additives on an extruder to make tailored products, which can then be used for standard injection molding, extrusion, and even for 3D printing applications. However, as already mentioned earlier, the compounding route can be challenging in terms of machine setup and places high requirements on the scrap that can be used. And let me explain this in a bit more detail, since compounds are a key element of today's presentation. So how do we get from composite scrap to compounds, and what is to be considered from a technical perspective? And please remember what I've mentioned earlier, we are doing this process together with experienced recycling specialists, which are supporting us with the right equipment and know-how. The first picture here shows a roll of unidirectional tape waste, which is the starting point of the process. And the first thing to keep in mind is that size reduction of composite waste means also size reduction of the containing carbon fibers. For high stiffness of the final product, the fiber length has to be retained as much as possible. On the other hand, based on your compounding equipment, only a certain size of scrap flakes can be used. Therefore, you need to find a sweet spot between maximum fiber retention and processable scrap size. As mentioned before, guillotine cutting is probably the best way to control this. And as also mentioned, the compounding equipment is key to being able to process the chips in a proper fashion. Most important is the feeder, which transports the chips into an extruder and which is typically specifically designed for fibrous scrap or recyclates. The capabilities of the feeder define then, for example, the process efficiency and the maximum fiber loading that can be achieved. Ultimately, by blending the scrap with any type of polymer and additives, this is an optimal way to turn composite scrap into either fiber master batches or, much better, straight into the tailored products for different applications. And on the next slides, I want to highlight some of the general benefits that these products can offer for your application. The first thing to mention is that together with our partners, we have produced model compounds with 10%, 20%, and 30% in weight of fibers in order to test the property spectrum of carbon fiber reinforced polycarbonate. Also, all of the here shown properties and additional special needs for your application can be adjusted in the tailored product development. And another important message here is also that in our lab tests and scale-up trials, we have found no significant performance differences between compounds made from recycled composites and those made from virgin carbon fibers. So first and foremost, the clear advantage of carbon fiber is, of course, their high intrinsic stiffness and significantly lower density compared to, for example, glass fibers. With these attributes, carbon fiber reinforced thermoplastic allow for the design of lighter and thinner parts. And in the first graph, you can see product stiffness based on the containing fiber volume when comparing carbon and glass fiber. At the same fiber content, carbon fiber reinforced thermoplastics reach a much higher tensile modulus than with glass fibers. Or if you want to look at it from a different perspective, parts with a certain stiffness target can be realized with less fibers when switching from glass to carbon. As a consequence, since more glass fibers are required to reach a high stiffness, the flowability and processability of these materials can become a challenge. This then translates into the limits of, for example, achievable wall thickness and part design when comparing glass and carbon fiber reinforcements. When also taking the density difference of both fibers into account, as shown in the second graph, carbon fiber compounds offer a significant weight-saving potential, which is increasing with higher stiffness requirements, as shown on the right side. And lastly, when making products on the basis of polycarbonate, the polymer itself brings some additional benefits, which are typical for polycarbonate, like good toughness, high dimensional stability of an amorphous plastic, and high heat resistance. But there's more. While unfilled, glass fiber reinforced, or mineral-filled plastics are electrically insulative, carbon fibers add the ability to conduct or dissipate electrical charges. Electrical conductivity is an important ability of the material if your application requires, for example, anti-static behavior or EMI shielding, for example, in electrical circuit enclosures. Shown on the left side of the graph, with increasing amount of carbon fiber, the electrical resistivity drops, which means the conductivity goes up. Compared to that, the insulative materials on the right side have a higher resistivity and therefore no electrical conductivity. Another benefit that comes along with carbon fibers, reinforced plastics, is the ability to dissipate heat and therefore act as sort of a heat sink. This thermal conductivity comes in handy as well when you need to reduce the surrounding part temperature, for example, in electronic devices. As you can see in the graph, the thermal conductivity goes up with increasing amount of carbon fiber content as well. The combination of electrical and thermal conductivity makes this product class a useful addition to, for example, our thermally conductive but electrically insulated polycarbonates, such as Macrolon TC110FR, as shown on the right side. And lastly, besides offering a unique combination of mechanical, thermal, and electrical properties, carbon fiber-filled polycarbonate products bring additional aesthetic design aspects. Special molding techniques such as dynamic heating in combination with textured surfaces lead to outstanding visual effects as shown at the picture of a laptop cover here. The intrinsic anthracite color and cool touch effect makes these products even more appear to be metal-like. And with this, I would like to hand over again to Florian now, who will shed some more light on potential applications and what's possible beyond injection molding compounds.
Thank you very much. Thank you very much. My mute button. Hope my mute button doesn't make weird stuff now. Yeah, thank you very much. And I would like to make a short excursion to another way of how we bring value into our materials that we use from our waste. Is the way is we call it marble. And on marble is the way that we use our flakes, which are made during this recycling process, and make something new from this. So the first way of doing this is what we call marble PIR structural, where we really use the flakes with long carbon fibers in it to bring structural properties into new parts. Usually the things can be used for thick-walled cavities with quite varying wall thicknesses. And you have a good variety of wall thicknesses, of performance, and so on and so forth, where you can bring it into and use really the structural properties of the carbon fibers in those parts. However, you have to be aware that these also thick wall thicknesses, which you can realize, require long cycle times. So for products where cycle time maybe is of less importance, those solutions might work. And this is for the structural applications. Another way, which we hear quite often, is that the designers are really, let's say, almost desperate for new ways of new carbon looks. So they want to show carbon fibers, which is good, but they want to show something new. And they also love to show something recycled. And that's where we think it might be a good path forward, is on the marble PIR aesthetics, where we use those flakes, press them to sheets, and use those sheets then for visible parts. The thing here is this recycled looks comes to the fact that there are certain variations definitely in the flake size, because it's based on recycled and waste, so it's not really distinct with other things you can do. However, you have to be aware that there are certain challenges on realizing the parts. It's the reproducibility according to the flake sizes. So it's how to specify this. And one key challenge that still needs to be solved is definitely the coatability of those flakes later on, which is an ongoing work. Another way of doing this, which is already about to be finalized, is the marble aesthetics based on virgin tape flakes. It's again also this novel way of carbon look. They can go for flake sizes with quite distinct aspect ratios and length. And here, for realizing part of this, you need a certain processing know-how, but this is something that could be very well learned. But this is maybe not yet the recycling story. Coming back to the compounds, because this was only a short side story on this. On the compounds, we were wondering where this material can be of help, because we were looking from our internal point of view, what are the properties of such a compound, but properties to maybe not really directly answer questions that you might have, or the issues that you might have on parts. So we're looking on certain problems, issues on parts that might occur, and where this material can be of help. Since it's a carbon fiber-based material, it should definitely be focusing on structural parts. And they were thinking about my mute button switched on. We're thinking on what could be properties for structural parts, or questions on structural parts. So one thing on these parts is always you have a high wall thickness and a high weight on structural parts. With the high stiffness and the good flowability of this material, you can reduce the wall thickness and the weight of these parts. And when you reduce the wall thickness, you can already answer the second question. You can save the space of your structural parts. You can make them thinner. You can make them lighter. And this is, again, due to the fact of the high stiffness and the good flowability of those compounds. One thing we learned from the laptop industry is that polycarbonate is material of choice due to the high dimensional accuracy of those materials. For example, for the battery housings, because you need these high accuracies there. And with these compounds, you have a very low CLTE. You can even increase the dimensional accuracy of those materials. So if you have structural parts which require a certain dimension accuracy, this material can be of help. Or sometimes you have maybe dust problems or static problems on your parts. This material can be of help here too, because it's electroconductive, and this is already an anti-static property that can be helpful for this. Look on different battery topics, because this is part of all these disruptive changes, I think, in all industries. EMI shielding, as Tim explained before, is one of the properties you can add to your structured parts with those compounds. And last but not least, a mix of perceived quality and technical properties is if you want to go for cool touch of parts, which is good, which feels quite valuable. The thermal conductivity could help, or from a technical point of view, if you want to dissipate some of the heat inside of parts, of electric parts, for example, here again, the thermal conductivity could help to improve these structural parts. So this is all questions on the problems you might have, might have on parts, or issues you might see where these materials can be really of help. The other question was, what could be potential applications where this material could be used for. This is most probably one of your expertises in the audience. However, we were thinking on this as well, trying to give some examples for inspiration about this. So the first thing is thinking on high-end hand-carry parts. High-end because definitely we go for a carbon fiber material, which is a high-end material, and hand-carry parts means you need something pretty lightweight, and weight saving is one of the key needs of those parts. One example we are thinking of could be these transportable batteries, or the cases for those transport batteries. So every gram you could save on those batteries is definitely helpful to increase the value of those parts and the usability of those parts. And the action we take here, or the solution we bring here, is reduce weight and space of these covers. This could be one potential application for those materials. Sticking on the batteries, for sure, a classic application is battery protection. So for battery covers, because we have this EMI shielding, we have these structural properties, and that could definitely help to protect batteries with this battery cover. And a third application, which was also in the picture that Tim has shown before, could be display back covers. Displays are very often hand carried, so you need lightweight. There's a competition in making screens thinner and thinner. So if the back cover requires more space, you need you want to make it thinner, and here it could definitely help. And with these structural and thin wall properties, here again, this material could help to reduce weight and space of those materials. And last but not least, and there should be for sure plenty more, this is only for inspiration, it could be on stiff thin wall parts, where you need a very low wall thickness, but a wide leverage, for example, like on propellers or lamellars. With this very high stiffness, you could increase the size of those parts. And with this, you could increase the performance per weight. And there are, again, these properties of lightweight and stiffness definitely of help for those parts. So these 4 examples should really, as I said, only give you inspiration. And we're now looking on the summary of what we've presented today. We can show that we've developed a material that can cover a lot of quite interesting properties, particularly when you compare it to kind of working house of our PCGF materials. So you have a much higher stiffness with these PCRCF that you could achieve. You can increase the dimensional stability significantly more. Plus, you can have a thermal conductivity with this material. You can have an EMI shielding with this material, and you could achieve maybe similar properties on the flame retardancy. But the question is this all? And this is a rhetoric question. The answer is for sure no. Because this was for us the starting point of this story and of this journey. For us, it's more that we talk together to make the material or tailor the material together to also add the requirements that you have onto this material. And with this, I would like to thank you for your attention and open the stage for Q&A.
Florian, Tim, many thanks for that. That was excellent. I've got some questions to start with. So the first question is from Jerome. I do not see the problem of disposing waste if it is made sure that it does not make any harm.
Maybe I take over. Short answer, yes. Longer answer, no. So it's not an issue. So it's but if you can recycle the materials, if the value of the material and the LCA properties of a material are higher by a reuse, that's for sure much more beneficial for material. And now thinking on that, there's the high value carbon fibers in there. Yeah, it's a pity to just dispose these carbon fibers. So it makes a much more sense to really bring them to a new life. To keep the value inside the material.
Thank you, Florian. Guys, we've just had a attendee just ask the question. Are you happy to share a copy of the PowerPoint presentation after the webinar? If you are happy, is it okay if the attendees drop you both an email? Are you okay with that?
Yeah, makes sense.
Okay, ladies and gentlemen, please do, you can see Florian and Tim's email on the right-hand side there. If you would like a copy, a PDF version, I'm guessing, of the presentation, please do take their email down and drop them an email. I'm sure the guys will come straight back to you, which I know they will. Okay, next question for you both. Can you explain the weight-saving potentials and how did you calculate them in detail, please?
Yeah, I can definitely take that. So maybe I was a little bit fast on that slide. So basically, the weight saving potential is derived from the density difference. So the density at a certain stiffness level, at a certain amount of tensile modulus, you just compare by percentage the difference, and you assume that your part has the same volume, basically.
Thank you, Tim. Another question here. Your presentation touches on new products from recycled composite production scrap. Earlier, there was a presentation on Desmopan. Are you able to create new products from recycling Desmopan, even though it's already a recycled TPU?
Yeah, so I will take that again, or you go ahead.
Tim, go ahead.
Okay, so I would like just to share my opinion on that. I mean, TPU is certainly more tricky than polycarbonate since it's still reactive somehow. As Florian mentioned in the introduction of composite, I mean, composites can be based also on TPU matrix material. In principle, the carbon fiber of that composite can be used, but if the products and in which dimensions new products can be made from that, it has certainly be to evaluate it. But I mean, in principle, technically it's possible, but one need to check on the properties that need to be achieved.
Anything to add, Florian?
I think that hits it. So if there's a concrete question behind this, I would also say please drop an email so we can maybe discuss. Maybe there's a certain rationale on that question. So we could think on that.
Thank you very much, Florian. Tim. Next question for you both. You claim such a high flame retardancy on your Masio tapes. What level of FR do you think you can achieve with such a compound?
Yeah, so another one for me. So the advantage that we're using polycarbonate as a resin material is its intrinsic wood flame retardancy. So we can definitely use that and tailor our products. So we are specifying our materials according to UL 94, and a V0 material is certainly possible. So excellent flame retardancy can be achieved. If you're interested in more details, just drop us an email as well.
Thank you, Tim. Another question for you both. Can this material be used to produce wearables for the medical industry?
Short answer, in principle, yes. again, depends on the specific needs for these applications. And of course, medical applications are always a bit tricky due to the underlying requirements for the feedstock and additives. So it needs to be checked carefully.
Thank you, Tim. Question here from John. You have examined applications that need good dimensional stability, but surface durability, e.g. tooling, workbenches, industrial equipment, e.g. impellers for heat pumps.
Good question. I'm a bit stuck on details. We're not sure where the answers. I think it's finally depending on the exact requirements on that. So we haven't examined that so far. So we do not know the real requirements. So this is a bit why I'm stuck. So for now, difficult to answer from my end.
Okay, not a problem. Tim, anything or?
No, it's fine with me.
Okay, right, another question for you both. John has just said a PU needs tooling. Does that mean anything? No. Okay, next question. Okay, no problem. Could this material be applied on railways for fire protection? Is it EN 45545 certified?
Good question. We haven't looked into that.
Okay. Another question. LCA. Did you do an LCA on these products?
I take this over almost. So this is currently ongoing. So we prepared the internal LCA part on this and need the external review for the approval of what we've done internally. This is going to be available pretty soon, I would estimate.
Yeah. Tim, anything to add?
No.
No, perfect. Okay, I'm just waiting to see if we have any more questions typed in. Any more questions from the attendees? Because we've been through the ones that have been typed in. I'll give them... guys, is there anything else you wanted to add?
Just maybe on this workbench story. So what we've learned, maybe I think on the tooling, so I'm not yet fully in all these details, but just a thought. So 3D printing of these large scale 3D printing is something that's going to be elaborated on. That seems to be quite well work and suitable for this. Because there was a question of PU needs a certain tooling. So for the 3D printing of large scale, you don't need tools. Maybe it's going toward that direction. So we can really 3D or print structural parts on large scale is something that's going to be examined on that.
Okay, Florian, many thanks. John's come back with another one. The question is, 20 years ago, I was trying to recycling pre-pregs using DMF solvent. Any developments on the solvent?
Okay, I will take this question. So we haven't looked into chemical recycling. Yeah. So by dissolving the matrix, for example. So we're just focusing on mechanical recycling. However, there are work streams looking into chemical recycling of in general polycarbonate compounds, but not for this composite case.
Okay, many thanks. I think that's we've got no more questions here. So, right, okay. Guys, many thanks for your time. I really appreciate it. It was a great webinar. And I'm just going to wrap up. So, ladies and gentlemen, once again, I would like to say a big thank you to Florian and Tim from Covestro for an excellent presentation today. Just to let you all know that today's webinar will be on demand for you to rewatch as well. Thank you to everybody for attending. We really do appreciate your time. And guys, many thanks again. Have a good week and a lovely weekend. And we look forward to seeing you all at our next We Automotive webinar. Thank you all. Take care. Thank you, guys. All the best. Bye-bye.